Ever wondered what any of these are, where to find them, or how to visualize them? We're about to find out. In this video, we'll take a look at the unit circle and break down its key components. First, take a look at this wheel, and specifically the yellow dot there. If we draw a horizontal axis through the centre of the wheel, you can start to think about how that dot changes height as the wheel rotates, or its vertical distance from that central axis. Drawing another axis that passes vertically through the centre of the wheel, we can see the yellow dot at its highest or lowest point on this vertical axis. That might seem pretty intuitive, if not obvious, but what happens between those points? Let's take another example with this watch to get a sense of what's happening with the angle change at the centre. Here, the second hand, which has been reversed and sped up slightly, acts as our unit radius, moving in the same way as the yellow dot on the wheel. When the hand is at 1, the angle, which all mathematicians love to call theta, is defined as this measure of turn between the horizontal axis from the 3, which is our starting point, and the second hand, the moving radius of our unit circle. Since the clock face is split into 12 equally defined points, the angle between each numbered marker is 30 degrees, since 360 divided by 12 is 30. But wait, we're dealing in circles, and circles love pi's, so in terms of radians, which is just a measure of turn in terms of pi, the total distance around our circle is 2 pi, because our radius is 1 unit. Overlaid on top of this image of an artwork by Rebecca Horn, you can see more clearly how we can start to define radians as an amount of turn, or the arc length of a unit circle in terms of pi. On the left we have pi and 2 pi radians as a half and full circular turn. And on the right we have half pi and 3/2 pi as a quarter or 3/4 turn. So when we're talking about 2 pi r as a standard formula for a circumference, this is where it comes from. Our radius in the case of the unit circle is just 1, so that r effectively disappears. And we can divide down further and further depending on how specific we want our radian measure to be. If we think of this CD as having a radius of 1 unit, then we can mark out a line of 6 units like this. Rolling the CD from the first point, starting with the radius is tangent to the horizontal, a full turn of the CD brings the radius back tangent to the horizontal just after the 6, at 2 pi. Now let's flip back to the wheel, as I want to show you how you can see a sort of delay in the height change as the yellow dot rolls around. This happens when you squish the video horizontally. Watch the right hand wheel near the top and bottom, and you'll see it has this slowing down sensation that you often feel at the top of a roller coaster. If we graph this height change of the yellow dot against our angle change at the centre, we'll get something like this. So this is a sine wave. The purple curve traces the height change of the line running vertical from the point where the moving radius touches the circumference to the x-axis as the angle theta increases from 0 to 2 pi. You might have come across the mnemonic SOHCAHTOA, but the sine of an angle, the SOH, is defined as the opposite over hypotenuse. This relationship is built from the unit circle, because our hypotenuse, as we've mentioned, is 1 unit, the radius, so our opposite is the height of the right angled triangle, created from this moving radius. As theta increases from 0 to half pi, the height gradually increases from 0 to 1, then dipping back towards 0 between half pi and pi. From here it descends from 0 to -1, until at 3/2 pi it starts rising back up again as the angle takes a full circular turn. When it's passing through the x-axis at pi, its gradient is much steeper than at its peak or trough of the wave, where the height change slows down like that roller coaster effect. In the same way we thought about the height change of an angle, we can also think about the change in the length of the horizontal line formed in the x-axis. This length, called cosine theta, runs from the centre of our unit circle to the point that meets the vertical sine length. Overall, the radius alongside these two lengths of sine and cosine theta create this right-angled triangle within our unit circle. And graphing the change in cosine theta as the angle changes gives us a similar looking curve, only it seems to have been shifted slightly. This can be better visualised as a graph running upwards from the circle, so that the change in cosine theta corresponds to the cosine wave. Here you can see two of the same graphs in two different orientations. Now putting both sine and cosine waves together looks like this, where you can see how the cosine wave is the same formation as the sine wave, only shifted by half pi to the left, and where sine theta starts at 0, cosine theta starts at 1. So to recap, what we're graphing is effectively the lengths of these purple and red lines, the sine and cosine of theta, that relates to the angle change at the centre. Although we're focusing on 2 dimensions for this video, I want to shift into 3 for just a second. It can be interesting and maybe more familiar to think of these functions of sine and cosine as extrusions from a circle, like the spring in production or a slinky. It has that circleness that you recognise from one angle, and also this familiar wave formation combining the height and width changes of sine and cosine when viewed from other angles. So graphing together sine and cosine in 3 dimensions, you might start to see the relationship between the mathematics and applications in the real world. Okay, now dropping back to 2 dimensions. So we have this basic setup. Our circle, a radius, the point where the radius meets the circumference, our sine theta and our cosine theta. One thing to note here is that because we have a right angled triangle, we have a relationship between sine, cosine and the unit radius from Pythagoras' theorem. This is a handy trig identity, where 1 squared equals sine squared theta plus cosine squared theta. From this basic setup, we can now add a whole bunch of lines to create even more trig functions. Although some might be considered overkill, this can be a handy toolkit to refer to. The one you're most certain to encounter is tangent, the final part of the Secant mnemonic. A line tangent to a circle means it would just touch the edge of that circle at a single tiny point, running 90 degrees perpendicular to the radius of that same point. For our purpose with the unit circle, the tangent is defined as the length of the line running from the point on the circle that meets the unit radius and the x-axis. Equally, it can be also thought of as the gradient or slope of the moving radius. The rise over run as sine theta over cosine theta. Notice on this animation how the tangent, defined in pink, shoots off into the distance before flipping sides at the top and bottom of the circle. At the points just before this happens, it's still reaching the x-axis if we could see far enough across. When the point on our circle moves through 1 or -1 on the y-axis, it's classed as undefined, since the line tangent to the circle at that point is also parallel to the x-axis, and therefore has no definable length to measure. And if you want some extra confirmation of this, try tan of 90 degrees or half pi on your calculator and see what happens. Now, let's look at some reciprocal trig ratios. The cotangent can be found to the other side of our point on the circle. This red dashed line that's defined as the length between the y-axis and the point on our circle. The cotangent is effectively the reciprocal of tangent, meaning 1 over tan theta, which we can also write as 1 over sine theta over cosine theta. And we can then rewrite this as cosine theta over sine theta. Because our tangent line creates a right angle with our unit radius, we can look at this right angled triangle for another trig function. The length between the origin and the point where the tangent meets the x-axis is defined as the secant, which is the reciprocal of cosine theta. And because we have a right angled triangle, we can define this relationship between the radius, tan theta and secant theta in terms of Pythagoras again, where sec squared theta equals tan squared theta plus 1 squared. The other reciprocal function is cosecant, or 1 over sine theta, and it's defined as this length running from the origin to the point where the cotangent line meets the y-axis. So sine and its reciprocal cosecant are here, cosine and its reciprocal secant are here, and tangent and its reciprocal cotangent are here. With this overview, you might notice how each function and its reciprocal can be formed on the same line as each other, with either a vertical, horizontal or tangential length. It should also be noted that these lengths are mirrored in either the x or y axis, depending on which quadrant the unit radius is in. So hopefully that's given you a bit of insight into where these trig functions and their identities come from, and maybe a more intuitive way to visualise circular motion. Like and subscribe for more maths related content, and thanks for watching.